Hello, thank you for watching, and welcome to the next video in my series on basic statistics. Now, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, and you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can get through it. I have faith in you. Many other people around you have faith in you, so should you. Number two, please feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist, because that does encourage me to keep making them for you. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when we make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over the basic concepts, and I will be doing so in a very slow, deliberate manner. Not only do I want you to understand what's going on, but also why and how to apply it. So all that being said, let's go ahead and get started. So in the videos immediately before this one, we talked about confidence intervals. And in the videos before confidence intervals, we talked about things like point estimation and the standard error of the mean. So in this video, what we're going to do is actually turn part of that on its head. So when we were finding confidence intervals in the previous video, we chose our sample size. We chose the level of confidence we wanted to use. And then using that and the population standard deviation, we calculated a margin of error. Now in this video, again, we're going to flip that upside down. So instead of choosing a sample size and calculating a margin of error, we're going to be given or select a margin of error and then calculate the sample size needed to find that margin of error. So again, instead of choosing the sample size to calculate the margin of error, we're going to choose the margin of error and then have to calculate the sample size necessary to do that. So all we're doing is we're rearranging a few terms in our margin of error formula to solve for something different. It's nothing more complicated than that. We're just rearranging the terms in the formula to estimate or find the necessary sample size. So let's go ahead and see how that works. So just a quick review of the margin of error. So when we are estimating some population parameter, we use sample statistics. So if we want to know the population mean, and we cannot go out and do it because maybe it has 1 million people in it or 1 million objects in it or whatever it might be, we use a smaller sample to estimate that parameter. So again, the sample mean is the most common. But again, the sample mean is never going to be perfect. It's going to always have some error component based on the fact that we're not including everything in the population to calculate it. So the best we can do is have some point estimate like the sample mean plus or minus some margin of error. Now in previous videos we talked about what influences or impacts that margin of error. The most notable one is the sample size. So in the previous ones we would choose our own sample size, and then that sample size, based on some other criteria, would then determine how wide or how narrow our margin of error was. So in this case, like I said, we're going to turn that on its head, and we're going to be given a margin of error, and then we want to find the sample size instead. So remember that the general formula for this was the sample mean, x bar, plus or minus the z, alpha divided by 2. Now remember, that is just the boundary of our confidence interval. So if we want 95% confidence, that would be plus or minus 1.96. That's the most common one that we use, so that's all that is there. So sigma, again, is the population standard deviation, or its estimate, divided by the square root of n. And of course, n is the sample size. Now in this video, what we're going to do is we're going to kind of forget about the left half of this expression. So we're not really interested in the mean per se. We're really focusing on this margin of error term on the right. So we're going to chop off the left side, and we're going to be interested in the right side. Now what we can do is give that its own little variable here, e. So e is the margin of error, and it's made up of these components over here on the right. So the z, alpha divided by 2, times sigma divided by the square root of n. So again, we're just taking the margin of error kind of all over on its own, and then we're going to work with it sort of on its own terms, literally. So remember that z alpha over 2 is just the z boundary of our interval probability. Again, if we're interested in 95% confidence, that z will be plus or minus 1.96. That's the most common one. And the sigma divided by the square root of n, remember, is the standard error. And again, we went over that in great depth in previous videos. So what can we do here? Well, if you look at this term over here on the right, or this expression, I'm sorry, over here on the right, we have four pieces. We have e, we have z, alpha divided by 2, we have sigma, and we have n. So if we have any three of those, we can find the fourth. And again, that's just basic algebra. So in this case, we can choose our margin of error, e. We would choose our confidence interval, most often 1.96, which is 95% confidence. We are given, or we estimate, sigma. And then based on having those three things, we can algebraically solve for n. So that's all we're doing. We're just rearranging the margin of error expression we already know to, instead of being given n and finding e, we're going to be given e and we're going to find n. Let's go ahead and look at how we would rearrange this to do that. So what we can do is use basic algebra to do some rearranging. So if we want to be solving for n, we need to isolate n. So what we can do is we can multiply both sides by the square root of n and divide both sides by e. So we basically just swap e and the square root of n there. Now we want to get rid of the square root sign, so we would square both sides to eliminate that square root. So when we do that, we have n equals, and then every term over there in the right is just squared. So we have our interval squared, which is the z alpha over 2, that's squared. Sigma is squared, and then e is squared. So to get rid of the square root sign, we square everything, and that's what we have over here on the right. So now we can solve for the sample size n using these other three measures that we are given or that we choose. And that's it. We're just taking the expression we already know for the margin of error, rearranging it so we can solve for n. So a little bit of note about sigma. So as I mentioned in many other videos, when we solve for the sample size, it really requires the population standard deviation sigma. Now most often we do not know it. So we have to use an estimate, or what's called a planning value, in its place. So here are a few options to do that. We can estimate sigma from previous studies that used the same population of interest. So many research studies are about sort of replicating some other person's study. So if there is agreed upon population standard deviation within the research literature, we can go ahead and use that for ours. So we will not always be the case, or there might be some industry standard if you're working in business. So again, you just have to look at what data you have, what previous studies there might be, or something of that nature. But that's one option. We could conduct a pilot study to select preliminary sample, and then we could use that sample standard deviation from the pilot study. That's another thing we could do. Again, if you don't know something, anything that's even relatively empirically valid is a lot better than just guessing. So if you can figure out how to be better, or a lot better than just a guess, you're doing much better than you otherwise would. So we can use these two examples to do that. Now, another one is just a judgment or best guess for sigma. So a common guess is the data's range, so its highest value minus its lowest value divided by 4. So if we don't have anything else to go on, we could do this last resort best guess, just the range divided by 4. But hopefully we have one of the first two before we go to this, but if all else fails, we can use this as our best guess. If you're writing a report or using it in a paper or something like that for school, I would just point out that this is what you're doing so your reader knows that, but hopefully it will not come to this. Let's go ahead and look at our first example. Okay, this is sort of an abstract example, and then we'll use some actually real-world scenarios in the other 3 examples. So we're going to do 4 examples total. So the question is, how large a sample should be selected to provide a 95% confidence interval with a margin of error of 8? So we are given our confidence interval and our margin of error. Now we're told to assume the population standard deviation sigma is 36. So remember, on our distribution here, what we're interested in is 95% of the probability being within our margin of error. So the margin of error is our boundaries there where the black lines are. So we can go ahead and just remember, I didn't point this out, I should have, that when we say 95% confidence, that is an alpha level of 0.05. So 1 minus 0.95 is our alpha. So alpha is just 0.05. Now we can set up our margin of error down here at the bottom. So in the middle, we'll assume our population mean, mu, is there in the middle. And then we have minus 8 to one side and plus 8 to the other side. So that is our margin of error on our graph. And that corresponds with where the black lines are, the boundaries of the actual distribution. Now here is our formula that we sort of solved for in the previous slide, so it shouldn't be too complicated at this point. Now all we do is substitute back into the formula. So remember, the boundary for 95%, the probability of 95%, is 1.96. So we go ahead and substitute that back into the formula. So again, notice the z of alpha divided by 2 for alpha is 0.05. That's just in the distribution table. If you go look at it in the front or back cover of your book, if you go down in the column and find that probability, you'll see that the z score is 1.96. So again, we went over that in the previous video. I'm not going to go over how to do that in this one. I'll just in your mind remember that if you see z and 95%, just remember in your mind 1.96. Okay, so sigma is 36, so we go ahead and square that, again, just by substitution. And then in the denominator, we are told that our error is 8, so we go ahead and square that. So we go ahead and do that computation, and we come up with 77.8. So the question is, how do we kind of interpret that? And again, we'll look at it in detail in the next slide, but just a quick interpretation is this. To have 95% of our sample means contain the population mean mu, each sample needs to be 78. So how will this actually work in real life? So if we wanted to have a margin of error of 8, given 95% confidence, and the population standard deviation was 36. So we would go out and take a sample of 78. And then using that sample, we could have a sample mean with a confidence interval, 1.96 on either side. Then we would go out and take another sample. Then we would go out and take another sample. And then we would go out and take another sample, all of size 78. And what we're saying is that if we do that over and over and over and over again, 95% of those samples will contain the actual unknown population mean. And when we're talking about confidence intervals, that's what we were meaning. That's the way we interpret confidence intervals. It's the percentage or the probability of samples that contain the actual population mean. So, the question we are really sort of asking ourselves is, what sample size is necessary to produce 95% confidence that the sample mean is within 8 of the true population mean? So remember, when we were talking about before, 95% of our samples containing the true population mean, this is the other way we can say that. So, 95% confidence that the sample mean is within 8 in either direction of the true population mean. So again, remember, as we increase sample size, we reduce the standard error, and our sample most likely becomes more representative of the population. So if our population has 1 million elements in it, what is better? We take a sample of 4 or a sample of 400? Which sample do you think will capture that population better? Well, I would say the larger one, the sample size of 400, will be more representative of the population than one that is size 4. And again, that should make intuitive sense to you, hopefully by now. Now, in graphical terms, here's what I want you to think about. Okay, and I wish I could do complex animations in these videos, but at least right now I cannot do that. So I want you to picture in your mind what's happening here. So we use the margin of error to set up a lower and upper boundary. Then what happens is we increase the sample size sort of incrementally, okay? As we increase the sample size, think of the bell curve. As we increase sample size, we, of course, are reducing the error. So what that means is that we're pulling the distribution up in the middle, and it comes in on the ends. So let's say, think about pulling up a sheet, a bed sheet. If you grab it in the middle and you pull up, what happens to the sides? Well, they move inward. Okay, they move inward to where you're pulling it up in the middle. So when we increase the sample size, that's actually what we're doing to the distribution. We're pulling it up in the middle and we push it in on the ends. Now at some sweet spot for sample size, 95% of the probability is between our margin of error. So we sort of pull up in the middle of the distribution, it comes in on the ends, it comes in on the ends, it comes in on the ends, and then boom, at some point, 95% of the probability is between the upper and lower value of our margin of error. So what we're finding out is that sample size that produces that. That's exactly what we're doing, so think about that in your mind when you're trying to visualize it. Okay, example 2, gas problems. So when I was doing this video, I pulled some data. And according to the Chicago Tribune website, the average price of gasoline inside the I-294 loop was $3.99. So, based on preliminary analysis, the sample standard deviation is 5 cents, so 0.05. So again, we have our $3.99 average price, and then we have our sample standard deviation of 0.5. So we wanted to determine an average price with some confidence. So recommend an appropriate sample size to determine a margin of error at 95% confidence. So we're going to look at plus or minus 5 cents, plus or minus 3 cents, and plus or minus 1 cent. So again, we're going to be talking about sample size in this problem. So again, here's our formula we've been using. So let's just take a look at what we know based on the problem here. So the z alpha over 2 we already know. It's going to be 1.96. The sigma we are given in our problem. So 0.05. That'll be our sigma down there on the right. And then E will change based on whatever interval we're trying to figure out. Whatever margin of error we're looking at. So E will change in accordance with A, B, and C over here on the left. So here are our margins of errors we're interested in. Here's our formula on the right. Notice I color-coded E to be red because that's what we're changing each time. So if we go ahead and substitute this in for all three, notice everything's the same except for the E in the denominator. And those are our margins of error over there on the left-hand side. So when we solve for these, for a margin of error plus or minus 5 cents, we would only need to select four gas stations. If we wanted to be plus or minus 3 cents, or within 3 cents, that is 11, a sample size of 11. What about within 1 cent? Well, that would be 97 gas stations. So what is going on here? Well, if you notice, as our margin of error decreases, our sample size has to increase to make up for that. So as we're less and less comfortable with a wide margin of error, as our margin of error becomes more precise or more narrow, we're going to have to select a larger sample size to accomplish that. Because remember, as the sample size increases, we're getting closer to the actual population mean we are interested in. So, margin of error and how it's related to sample size. So example 3, car production. So a quick look at production data over the past month revealed that a global auto company produced a low of 782 and a high of 1,303 automobiles per hour. So over the past month, we broke it down into hours. And what we found out is that the lowest number of vehicles produced during any given hour was 782. The highest number produced during any given hour was 1,303. That's our minimum, maximum, or range. So a 95% confidence interval estimate for vehicle production is desired. So again, we're going to use a 95% confidence interval. But we kind of have to do something else in this problem. So the first thing we notice is that we do not have a sigma. We don't have a standard deviation. So we have to figure that out. So what is the planning value for the population standard deviation? And then number 2, how large of a production plant hour sample should be taken with the following margin of errors? So if we wanted to take a sample of any given hour across the globe, how many of those samples will we have to take with the following margin of errors? So if we wanted to be within plus or minus 100 cars, plus or minus 50 cars, that margin of error, or plus or minus 50 cars. So those 3 margins of error. Let's do the first part first. So planning value, in this case, we're going to use sort of the number 3, the least desirable method of doing it. That is the range divided by 4. So the range is 521, that's just the highest minus the lowest, and then divide that by 4. So that's 130.25, and we'll just sort of round it down to 130. So that's going to be our sigma for this problem, because we don't have anything else to go on. Now we just repeat the process we did for the previous problem. So we go ahead and substitute the numbers in, and notice that everything stays the same except for the margin of error there in the denominator. So what are our sample sizes? So to be within 100 cars, to have a margin of error of 100 cars with 95% confidence, we would have to select 7 hours at random to find our population mean. So we would select a sample size of 7, another sample size of 7, another sample size of 7, etc. And what we're saying is that 95% of those samples, given their margin of error on the side, would contain the actual population mean. So the actual hourly production. the mean hourly production. Now, to get that margin of error down more, so plus or minus 50 cars, now we'd have to select sample sizes of 26. So again, with a larger sample size, it's going to be more representative of the average hourly production. So in this case, we would have to select 26 random hours throughout the month for each sample. Now, for plus or minus 30 cars, each sample would have to be 73. And again, this should make intuitive sense. To have a smaller margin of error, the sample size will have to go up, all else remaining even. So in this final case, each sample would have to be 73 random hours throughout any given month, so that 95% of our samples intervals contained the actual population mean production. Okay, and our final example, example 4, confident retirement. So a fictional survey by the U.S. Chamber of Commerce asked upper-level managers about their retirement investment practices. So based on a previous study, the Chamber assumed a planning value for the standard deviation of $1,500, and they wished to use $200 as the desired margin of error for the interval estimate of the population mean. So, determine the sample size for the following: a 90% confidence interval, a 95% confidence interval, and a 99% confidence interval. So, whoa, what's going on here? Remember at the very beginning I said that in that sort of expression where we had E equals so forth and so on and so forth, if we had 3 of them, we could find the 4th. So this is sort of an example where we're sort of changing what we are given and then what we're solving for. So in this case, the margin of error is not changing, okay? It's going to be $200. The standard deviation is not changing, of course. It's $1,500. So what is changing? The confidence interval is changing. So let's take a look at how this is going to work. So what we're changing here is the term up here in the red. So remember, that z, alpha over 2, that is the boundary of our probability. So when we're using 95% as our confidence interval, it's going to be 1.96. That's what we've been doing. That's what we're familiar with. So what we do is just change that in each one of these formulas. So if you go back and remember, we talked about how the z value or the boundaries change for different confidence intervals. So the most common, 1.96, is the middle 95% of the distribution. Now what if we're only interested in the middle 90%? What's going to happen to the boundaries? Well, it's going to move inward, and we're going to have more alpha out in the tails. That's why the z-score, the z-value, is 1.645. It moves inward from where the 1.96 is for 95%. Now look at 99%. We want to capture 99% of the area under the curve. So to do that, our boundaries are going to have to move way outward, and that's out to 2.576. So if you think of our bell curve with our blue area in the middle, as the confidence interval changes, what's going to happen is those boundaries are going to move in and out depending on the level of confidence we want to do. So how do we interpret this sort of in our mind? So what we're saying is that for 90% confidence, we're going to go out and take many samples, and we want 90% of them to contain the actual population mean. So that's what we mean by 90% confidence. Now for 95% confidence, that's what we've been doing. So we want 95% of our interval estimates, okay, our sample mean estimates, to contain the actual population mean. And then for 99%, that's just what it says it is. We want 99% of many, many samples to contain the actual population mean. So what do you think that's going to do to our sample size? Okay, so let's go ahead and do these calculations. So for 90% confidence, our sample size would have to be 153 managers that we would sample or interview, however you want to look at it. Okay? So, to have 90% confidence, our sample would have to be 153. And if we took that 153 sample over and over and over and over again, 90% of them would contain the actual population mean. Now, for 95% confidence, we would have to up that sample size to 217. So we would take many samples over and over again of sample size 217, and 95% of them would contain the actual population mean. Now, what about 99%? Well, in this case, our sample size would have to be 374. So our sample size would be 374, and given the margin of error of $200, we would have to say that 99% of those contain the actual population mean. So again, what we're doing is we are constructing a sample mean with the margin of error that we are given. And if you remember the previous video, we put all these samples sort of underneath the distribution curve. And what we said is that the sample, plus or minus that margin of error, either contained the population mean or it didn't. So when we're talking about 90%, 95%, 99% confidence, that's again what we're talking about. Whether or not that sample mean, plus or minus the margin of error, contains the actual population mean. So the most I want you to get out of this is the relationship between these three things: the confidence interval, the sample size, and the margin of error. Because usually sigma is given to us. So if you understand how these three things interplay, you really gain a wonderful, basic, foundational understanding of how stats works. So, all else remaining constant, when the level of confidence is increased, a larger sample size will be required. Because we're saying that more and more of our samples have to contain the population mean. So to do that, we have to take larger samples, make them more representative of the overall population. So a larger sample size ensures more sample means are within the given margin of error, due to the fact that larger samples are more representative of the overall population. So a larger sample size will be required under the following conditions: a smaller margin of error requirement. So that's what we did in the first sets of examples. We decreased the margin of error requirement. Okay, a little bit less, a little bit less, a little bit less, so narrower. As we narrowed the margin of error requirement, our sample size had to go up. A higher level of confidence. So if everything else stays the same, but we increase the level of confidence we want, that's also going to increase our sample size requirement. Or both. So we could narrow our margin of error and increase our level of confidence, and that would really jack up the sample size we would have to take to meet those requirements. So just a quick review and then we're done. So solving for the sample size requires the population standard deviation sigma. Most often we do not know it, so we have to use an estimate or planning value in its place. So remember our options: an estimate from a previous study using the same population of interest, a pilot study that was very good, and we used the sample standard deviation from that pilot study, or we used that judgment or best guess as sort of the last case scenario, the worst scenario if you only really have to do it, which is the range divided by 4. Now, a larger sample size will be required under the following conditions: a smaller margin of error requirement, a higher level of confidence, so 90 to 95, 99%, or both. So again, I really want you to understand the interplay between those three things: the sample size, the level of confidence, the confidence interval, and the margin of error, and how they all interplay with each other. Okay, so that wraps up our video on how to estimate the sample size when we are given the level of confidence we want and the margin of error that we want, and then usually the sigma is given to us in the problem, or we have to estimate it somehow. If you really have a firm understanding of this concept, it's going to prepare you for what's coming next, and that is hypothesis testing. So I'm sure you've probably heard of the null hypothesis and the alternative hypothesis and things of that nature. To do those things, you have to understand how sample size, margin of error, level of confidence affect the estimates we are doing for populations. So when we're doing hypothesis tests, we are testing whether or not a claim is within usually some margin of error. And actually, in the previous videos on confidence intervals, we were almost to doing hypothesis tests without actually saying we were. So if you have this under your belt, understanding how hypothesis testing works will be much easier. Okay, so just a few reminders. If you're watching this video because you're struggling in a class, stay positive and keep your head up. You are smart and talented. I know that. Everyone else around you knows that. So you should always keep that in your mind. Number 2, please feel free to follow me here on YouTube, on Twitter, or on LinkedIn. That way when I upload my videos, you know about them. Please give it a thumbs up if you like it. Share it with your classmates or your colleagues, or put it on a playlist. That does encourage me to keep making them for you. If you think there is something I can do better, please leave a constructive comment below the video, and I will try to take those ideas into account when I make new ones for you. And finally, just keep in mind that the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person, that is what really matters. I firmly believe that if you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching. I wish you all the best of luck in your work and in your studies, and I look forward to seeing you again next time.